So we're finishing the problem we started in the last video. So we're solving this series here. So since we're multiplying by 1, we essentially just need to work with what's in our parentheses. Negative 2 to the 6th is 64, so we have 1 minus 64 over 1 minus negative 2, which is 3. So this ends up with negative 63 over 3. So the values of our series is negative 21. Number 7. So we got these ellipses here. So we don't know the total number of terms yet. We know our starting value is 1/2. Our common ratio, we'll take negative 1/4 over 1/2. So our common ratio is negative 1/2. Using that, we can find our missing values. We'll get negative 1 over 16, positive 1 over 32, negative 1 over 64, and a positive 128 before we get back to the negative 256. So from that, we can see our number of terms then is 8. So plugging it in, S of 8 is equal to our A, 1/2, 1 minus our common ratio, negative 1/2 to the 8th over 1 minus negative 1/2. So this gets us to 1/2 times 1 minus 1 over 256 over 3 halves. So that's 1/2 over 255 over 256 divided by 3 halves. From here, we'll get 1/2 times 85 over 128 once you plug that into your calculator to get us our final answer of 85 over 256. So we can do some modeling with these. So some financial problems specifically can be modeled by a geometric series. For instance, an annuity involves equal payments made at regular intervals for a fixed amount of time. Because money can be invested and earn interest, comparing the value of money today to the value of money in the future requires accounting for the effect of interest. The future value of an annuity is how much the annuity payments will be worth at some point in the future, whereas the present value of an annuity is how much the annuity payments are worth in the present. Although an interest rate is typically expressed as an annual rate, it can be converted to a rate for other periods of time. So for instance, an annual rate of R% results in a monthly interest rate of R over 12%. So in general, if interest is earned N times per year, an annual interest rate of R is divided by N. So we have Niobe saving for a down payment on a new car, which she intends to buy a year from now. So at the end of each month, she deposits $200 from her paycheck into a dedicated savings account, which earns 3% annual interest that is applied to the account balance each month. After making 12 deposits, how much money will Niobe have in her savings account? So she's interested in future value of her annuity, future value, of 3% annual interest rate corresponds to 3 over 12% or 0.25% monthly. So first calculate the sequence of end of month account balances. Recognize the recursive nature of the recursive nature of the calculations. What you have this month has to depend on next month. So the end of month balance for month 1 is $200 because the first deposit of $200 is made at the end of the month, but the deposit doesn't earn any interest that month. The end of month balance for any other month is the sum of the previous month's end of month balance and the interest earned on the previous month's end of month balance and the next deposit. So if B of M represents the account balance for month M, then a recursive rule for the account balance is B of 1 is 200 and B of M is equal to B of M minus 1 plus B of M minus 1 times 0.0025 for that 0.25% interest rate plus 200, the new deposit she's adding. So notice you can rewrite the equation in this form using the distributive property. So plugging in values, we're finding those end of month account balances. So if we want to find the sum of the geometric series, we have to look at what our different values are. So you may find it helpful to use the commutative property. So in this case, we should know that our A value is 200. And so then our, I apologize, the common ratio is 1.0025. So whatever the original balance was, as well as that 0.25% interest value. So our A is 200. Our common ratio is 1.0025. And again, that's accounting for the original balance that she had added to that the interest. So the 2.25% interest rate. So then the number of payments is 12 because there's 12 terms. Plugging those in, you get that. Again, this is all calculator work. Probably best to do it in that order that they're showing you. Do the numerator first, and then divide by the denominator, and then multiply by 200. So that's showing you her account balance that she'll have after 12 deposits. So let's say she decides to postpone buying a new car because she wants to get a new smartphone instead. She can pay the phone's full price of $580 upfront, or she can agree to pay an extra $25 per month on her phone bill over the course of a 2-year contract for phone service. So what is the present cost to Niobe if she agrees to pay $25 per month for 2 years, assuming that she can put the money for payments in a savings account that earns 3% annually interest and make $25 monthly withdrawals for 2 years? So as in part A, a 3% annual interest rate becomes 0.25% monthly interest rate. So let's say she puts an amount M1 in the savings account and lets it earn interest. So for 1 month, she'd have 1.0025 M1 available to make her first phone payment. So since she wants that to equal 25, you have to set it equal. You'll find out that the amount she has to input is 24.94. This means that the present cost of her first phone payment is $24.94 because that amount of money will be worth $25 in 1 month after earning the interest. So let's say instead she puts M2, an additional amount M2 in the savings account, and lets her earn interest for 2 months. So then she'll have 1.0025 M2 after 1 month. And 1.0025 times 1.0025 M2, or 1.0025 squared times M2 after 2 months. So since she wants that value to be 25 instead, you can do 25 over 1.0025 squared to get 24.88. So this means that the present cost of her second phone payment is $24.88. It also means that she must deposit a total of those first 2 months to get $49.82 in the savings account in order to have enough money for her first 2 phone payments. So you can continue in this pattern all the way through the 2 years of the phone payments that she's going to possibly make. So if we can find the sum using our rules, so our initial value is 25 divided by 1.0025. Our rate is 1 over 1.0025, and it's over 24 months. So plugging in the values, it's to the 24th over 1.10025. So although Niobe will end up making total payments of $600, the present cost of the payments is $581.65, which is only slightly more than the upfront price of the phone. So it's really up to her. Probably the upfront price, again, would save her about $1.65. A lottery winner is given the choice of collecting $1 million immediately or collecting payments of $6,000 per month for the next 20 years. Assuming the lottery money can be invested in an account with an annual interest rate of 6%, which is actually really good, that is applied monthly, find the present value of the lottery's delayed payout plan in order to compare it with the lump sum plan and decide which plan is better. So come back for the next video and we'll work through how to solve this problem.